So in this session, we'll continue with the programmer's model of 8086 to 80486 processor. We are actually looking at a part of the execution unit only. This is in continuation with the previous session. If you have to understand what is happening in this session, you should have gone through the previous session completely. We are going to be looking at one of these registers which are present in the execution unit, which is the flag register. We need to look at it at little more detail because we have to understand what is the functionality of this flag register with respect to the ISA of 8086 or 286 or 386 or 486. So what we were looking at in the previous sessions, of course, is that the microprocessor's architecture can be broken up into two subsections. One which fetches the instruction, that is the BIU, the other which executes the instruction, which is going to be the EU. Now what we are looking at in this session in detail, of course, is going to be the flag register. The flag register is also a special function register because it is used for only one reason. It acts as a flag register, or it indicates the kind of results that you have got, or it's used for controlling certain operations of the microprocessor. Flag register cannot be used for temporary storage of data. It cannot function as a pointer register. It functions only as the flag register. And again, we have two different execution units or two types of execution units. One which is available with our 16-bit processors, that is 8086 and 286. These are 16-bit processors. Hence, the flag register also remains as a 16-bit flag register. In case of the processors which are above 286, that is 386 and 486, which are 32-bit processors, we have a 32-bit flag register which is called as the E flag register. So if you're looking at it from 8086 or 286 point of view, 16-bit flag register. From 386 or 486 point of view, it is going to be 32-bit E flag register. Now before we examine each and every bit of the flag register, because here every bit has a significance. It either indicates status or it indicates control. Let's look at flags in general. Flags can be of two types. They can be either status, which indicates the kind of result that you might have obtained because of an arithmetic or logic operation. And you have control flags which are used for controlling certain operations of the microprocessor. So we will be looking at both the flags, the status flag and the control flags. But what I'm going to show you is not just the 16-bit flag register. I'm going to show you a 32-bit flag register. The first 16 bits continue to remain the same, whether it's 8086, 286, 386 or 486. The rest of the 16 bits are available only in the 32-bit versions of the Intel family, that is 386 and 486. Okay. So the flag register, as I said, each and every bit is going to be significant. Here I've used a little bit of coloring scheme here. The bits which are indicated in black are available from 8086 processors onwards, and the ones which are indicated in blue are available from 80286 onwards. It's not just 80286, it's 80286 onwards. The ones which are indicated in red are available from 80386 onwards. The one which is indicated in green is available only in 80486 processor. So the ones in black available in all members of the family, the ones in blue available from 80286 onwards, the ones in red from 386 onwards, the one which is in green is going to be available from 486 only. And you can see that some of the flag bits have been underlined. Now the ones which are underlined are all status flags, meaning they reflect the kind of result you have obtained because of an arithmetic or logic operation, or because you have done some kind of data transfer. That could also affect some flags. So that is essentially the result of any instruction which is executed by the x86 processor. The ones which are not underlined, for instance the I bit or the D bit here, they are not underlined. So those are the control flags. They control the functioning of the x86 processor. Okay. Now, as I said, in flag register, every bit has a certain purpose. Okay. So let's examine the flag register bit by bit. The ones where no bits are indicated or no value has been written are the bits which are not used. You're not supposed to change the values of these, or you're not supposed to access these bits. The ones which have some value written in them are the only one which have any meaning as far as this 32-bit register is concerned. So let's start with the first bit, which is also called as the carry flag. Whenever you're doing any arithmetic operation, when you're doing an addition for instance, you might get a carry. When you're doing subtraction, there is a possibility of a borrow. So whenever your addition results in a carry, your subtraction operation results in a borrow, the carry flag is going to be set, indicating that your addition or subtraction has resulted either in a carry or it has resulted in a borrow. So as I said, the flags, if they are status, indicate the kind of result that you have got. So you have added two numbers, you have got a carry. The carry flag is set. You have added the number, no carry, carry flag will be 0. So these are bit by bit. So they can have only two values. One, which is the set condition or the true condition. The other, where the bit is 0, which is called as the reset condition or the false condition. So you can have a set or a reset. So the carry flag gets set whenever you are doing a arithmetic operation and that arithmetic operation results in a carry. This bit of course will not be of any significance whenever you're doing a logic operation, because when you're doing a logic operation there is no carry generated. This bit makes sense when you're doing an arithmetic operation and that arithmetic operation results in a carry, results in a borrow, then the carry flag is going to be set. Otherwise it is generally reset. The next flag which we are going to look at is going to be the parity flag. Parity flag essentially gives the number of ones which are present in the result. If the number of ones happen to be an even number of ones, then the parity flag is set. Even number of ones we know means even parity. Odd number of ones we know indicates odd parity. So if the result has an even parity or it has an even number of ones, if my result for instance happens to be 1 1 in hexadecimal. So if it's 1 1 in hexadecimal, I'm going to have 2 ones in it. So even number of ones. So the parity flag is going to be set, indicating that the result has an even parity. If my result happens to be 31 in hexadecimal, 31 would have 3 ones in it. 3 having 2 ones and the value 1 having 1 1 in it. So you have 3 ones. 3 ones means odd parity. So parity flag will be 0. Parity flag is set whenever the result has an even parity. If the result has an odd parity, the parity flag is going to be reset. So again, here we are talking bit by bit. So the bit can be set or the bit can be reset. The next flag which we look at is going to be the auxiliary carry flag. The auxiliary carry flag is similar to the carry flag. The only thing is it is going to indicate whether you had a carry when you were adding the data nibble by nibble. For instance, if I'm going to add data which is 0f plus 0, 1, your result would be 1, 0. But when you're adding f and 1, you're going to get the carry in the lower nibble. F plus 1 would give you 0 and a nibble carry of 1. So that causes the auxiliary carry flag to be set, indicating that you had a carry when you added the lower nibble of data. Now this auxiliary carry flag makes sense only when you're doing 8-bit operations. When you're doing 16-bit operations or 32-bit operations, the auxiliary carry flag doesn't have a lot of significance. When you're doing an 8-bit operation, you can break up your 8-bit data into 2 nibbles, the lower nibble and the higher nibble. The lower nibble, whenever you're adding it, if there is a carry, then the auxiliary carry flag is going to be set. The upper nibble of course will affect directly the carry flag. The lower nibble will be affecting the auxiliary carry flag. This is a flag which we will not use very frequently, but we will make use of it whenever we are doing BCD operations. So when we come to BCD instructions, we will have a look at how the auxiliary carry flag behaves in much more detail. Auxiliary carry flag has significance only when we are talking about 8-bit data, and it indicates that whenever you are adding the lower nibble of this 8-bit data, if you get a carry, the auxiliary carry flag is going to be set. So for example, here f plus 1 in the lower nibble would definitely result in an auxiliary carry flag being set. The next flag we are going to look at is the 0 flag. The meaning here is very simple. If your result happens to be 0, this flag is set. Result 0, flag set. Result non-zero, flag is going to be reset. So the flag essentially reflects whether the result is going to be 0 or not. When you're adding numbers, when you're subtracting numbers, you're doing logical operations, you can get a 0 result. So whenever you get a 0 result, the 0 flag is going to be set. It's used for all arithmetic operations, all logic operations. Whenever you get a 0 result, the 0 flag is going to be set. If you have a non-zero result, this flag continues to remain 0 or it remains in the reset condition. The next flag we will be looking at is the sign flag. Sign flag essentially actually reflects the most significant bit of your data. If you're talking about 16-bit data, it's basically going to reflect the D15 bit. With 16-bit data is D0 to D15. Whatever is the condition of D15 will be the condition of the sign flag. If you're doing an arithmetic operation, which results in a value which is going to be 800. So if it's going to be 800, your D15 bit will be 1. The D15 bit being 1 makes your sign flag 1. If you're going to get a result which is 7FF, D15 bit will definitely be 0. D15 being 0 will also mean that your sign flag is going to be 0. So when you're doing any arithmetic operation and you are going to get a result which has MSB as 1, sign flag will be 1. If your most significant bit is going to be 0, the sign flag is going to be 0. This is because the microprocessor looks at every data in the sign magnitude form. You would already be familiar with sign magnitude form because most of you have done digital design. So when you did digital design, you would have done 2's complement arithmetic. There you would have a look at the sign magnitude form of representation. In sign magnitude form of representation, if you are going to have 8-bit data, D7 is going to be the sign. The rest of the 7 bits are going to indicate the magnitude. If D7 happens to be 0, it is a positive number. If D7 is 1, it indicates it's a negative number. If it is 16-bit data, D15 is going to be the sign. D0 to D14 is going to be the magnitude. If D15 is 0, then your number is a positive number. If D15 is going to be 1, your number is going to be a negative number. Microprocessor looks at all data in sign magnitude form. So since it looks at it in sign magnitude form, if the MSB is 1, according to it, it is a negative number. And since it's a negative number, the sign flag is going to be set. If the MSB happens to be 0, as far as a microprocessor is concerned, the number is a positive number. And hence the sign flag is also going to be 0, indicating that it is the positive number. So this truly need not be the sign. It essentially is the reflection of your MSB. MSB 0, sign flag 0. MSB 1, sign flag 1. The next status bit which we will look at is going to be the overflow bit. The overflow bit is used to indicate whether a 2's complement overflow has occurred. For instance here, if you take this example, I am adding 2 positive numbers. 7F is a positive number. 01 also is a positive number. D7 bit is going to be 1. These are 8-bit numbers. D7 bit is 1. So since D7 bit is going to be 1, it means that you are going to be adding 2 positive numbers. 7F is a positive number. 01 is a positive number. I am adding 2 positive numbers. The result is going to be 80. Now as far as a microprocessor is concerned, if the MSB is going to be 1, it's a negative number. So it's not possible that you add 2 positive numbers and you get a negative result. This negative result was obtained because whenever we are talking about 8-bit numbers, the maximum possible positive number that you can represent is plus 127. The maximum possible negative number that you can represent is minus 128. But unfortunately, when you add plus 127, which is a positive number, with plus 1, which is again a positive number, you will get minus 128, which is going to be a negative number, which cannot be supported if you're talking about 2's complement arithmetic. So in this case, the overflow flag is set, indicating that a 2's complement overflow has occurred. A 2's complement overflow will always occur whenever you add 2 positive numbers and get a negative result. The other extreme is also possible. You're subtracting 2 negative numbers and you end up getting a positive result. That is also possible. So when you are working that way, you might also end up getting a negative result. So a positive result. So then also the overflow flag is going to be set. So these are the status flags which are available on all processors starting from 8086 onwards. So the status flags are essentially going to reflect the kind of result. Whether you have got a carry, whether your result is 0, your result has an even parity, result has an odd parity, whether result had an 2's complement overflow, all of these are going to be represented by the different flags. When we come to instructions, with each and every instruction, we will also see how these flags are going to be affected. We will see number of examples where we will see how these flags are going to be affected. Now we are looking at it from the programmer's model point of view. Now coming to the control flags, the first control flag we will look at is going to be the trap flag. Now if this trap flag is going to be set, it causes the processor, whether it's 8086 or 386 or 286, it will cause the processor to halt after every instruction, and is essentially it is raising a interrupt to the processor or stopping the processor after every instruction. This can be used by the programmer for debugging his program. So at the end of every instruction, the programmer can have a look at the contents of his registers. He can have the look at the contents of memory location to see whether the instruction has been executed properly or not. But then there is nothing actually associated with the trap flag which says that the registers would be examined or the memory would be examined. As far as the processor is concerned, if the trap flag is going to be set, it causes the processor to stop execution after every instruction. What the programmer does once the execution has stopped is left to the programmer. But essentially the trapping function or the trace function is used for debugging by the programmer, because the processor halts after every instruction. After every instruction, programmer can examine the contents of registers or memory location to see whether the instruction was executed successfully or not. So the trace flag is a control flag. If the trace flag is going to be set or the trap flag is going to be set, the microprocessor will essentially stop execution after every instruction. Now another control flag is going to be the interrupt flag. Interrupt flag is used to enable or disable interrupts. If the I flag is set, interrupts are enabled. If I flag is going to be 0, interrupts are going to be disabled. Now generally whenever the microprocessor executes instruction, it goes sequentially. It executes one instruction after the other. Now if you want to stop the sequential flow, one thing is you can use subprograms. You can call a subprogram, or an interrupt can be raised to the processor. Interrupt can be an external signal. It can be an internal error which caused an interrupt, or it could be an internal instruction which caused an interrupt. An interrupt when raised to the processor will stop the processor will cause the processor to stop whatever it is doing currently and branching to a different address, which is called as the interrupt service routine address or the ISR address. So whenever an interrupt is raised to the processor stops the sequential execution of instructions and resumes execution from a new set of addresses which are called as the interrupt service routine address. So if the I flag is going to be set, processor responds to interrupts. If I flag is going to be reset, processor will not respond to interrupts. So whether the processor responds to interrupts or doesn't respond to interrupt is determined by the I flag. I flag again is a control flag because it decides the behavior of the processor, whether the processor is going to respond to interrupts or not respond to interrupts. Again, we will be seeing more details on interrupts and how the processor behaves when an interrupt is going to be raised when we come to interrupt service routines. Another control flag is going to be the direction flag. Direction flag is used with string operations. So whenever we are talking about a string of data or array of data, you can parse the string from the first to the last data, or it's also possible you start with the last data and move upwards and go towards your first data. So the string can be parsed in either direction. You can go downwards or you can go upwards whenever we are talking about a string of data or array of data. The direction flag determines whether the string is going to be parsed downwards or whether it is going to be parsed upwards. So when we come to string instructions, we will also see what is the effect of the direction flag and whether the string is going to be passed downwards or whether it is going to be done upwards. We will also see that with string instructions. So direction flag is associated only with string instructions and determines the direction in which the string is going to be scanned by the processor, whether it starts from the first to the last data or starts from the last data and then moves upwards towards the first data. Now coming to the control bits which are not available in all of the processors, which are available only from 80286 onwards, you have two bits which are called as input-output privilege bit. Right now I'm just stopping with the expansion of these bits. These bits will not make any sense to you. They will only when we start with privilege mode of operations, they will make any kind of sense, or whenever we talk about protected mode of operation, these bits have a significance. So I'm not going to explain the function of these bits because right now you cannot understand this. You can understand this when you come to the protected mode of operation. So I will pick up these bits again when we come to the protected mode of operation. But right now, the input-output privilege level bits are going to be used in the protected mode of operation. They are called as IOPL or input-output privilege level bits. There is one bit which is used in nested tasking. Again, it makes sense only when we are talking about multitasking environments or we are talking about protected mode of operation. So again, we will not be examining this particular bit in detail. The next bit is available only from 80386 onwards, that is the resume flag. The resume flag bit essentially is used with your debugging operations. So once you begin debugging and you end with it, whether the processor should resume from the previous address or whether it should be resetted and start all over again is indicated by the resume bit. If the resume bit is 1, once debugging is over, it will resume from whatever address the processor stopped for the debugging function. If this is going to be 0, the processor will have to restart all over again. So resume flag is used essentially for how to exit from the debug mode of operation. There is one more bit in 80386 which is called as the virtual mode bit. Whenever this bit is going to be set, 80386 behaves exactly like an 8086 processor. This is called as the virtual 86 mode of operation. So this bit is set. 80386 is same as 8086. It behaves like a 16-bit processor. It supports only 16-bit operations and there would be no difference whatsoever between the behavior of 80386 and 8086 processor. So this is available from 386 onwards. Now another bit which is present from 486 onwards is actually the status bit. This is called as an alignment check bit. Now whenever you are storing 32-bit data in memory, and memory is byte organized. We talked about memory being bit organized where every memory location stores 1 bit of data. We talked about memory being nibble organized where every memory location stores 4 bit of data, and memory being byte organized where every location stores 8 bit of data. So if memory is byte organized, every memory location can store only 8 bits of data. In order to store 32 bits of data, you're going to require 4 memory locations, right? So the alignment check basically is used to indicate whether the 4-byte boundary is maintained by the processor whenever it is storing the result. The 4-byte boundary would mean that your first data is from location 0 to 03. The next data is going to be from 04 to 07 because when you're saying 00 to 03, the first byte is in 0. The second byte would be in 01, the next byte would be in 02, the fourth byte would be in 03. So we store one 32-bit data starting from 00 to 03. The next 32-bit data would hence come at 04, 05, 06 and 07. So you need 4 locations to store the 4 bytes of data. So whether this boundary of 00, 04, 08 and so on is maintained or not when the microprocessor is storing the result is indicated by the alignment check flag. If the alignment check flag is 0, then in that case the alignment is not maintained. If it is 1, in that case the alignment is going to be maintained. So again, it's a status flag. It indicates how the result is being stored by the microprocessor into memory. If it is stored with the alignment, then in that case alignment check flag will be 1. If alignment is not maintained, then this particular bit is going to be 0. So these are the various flag bits which are present from 8086 to 80486 onwards. Again, you have to remember that this register would be only the first 16 bits whenever we are talking about 8086 and 80286. The rest of the 16 bits come into significance only when we are talking about 386 or the 486 processor. So the flag register is 16-bit flag register in 86 and 286. It is going to be the 32-bit E flag register whenever we are talking about 386 and 486 processors. So just to summarize whatever we have seen over the last 5 sessions, the 8086 processor is essentially made up of 2 units, the bus interface unit and the execution unit. The bus interface units provides the required hardware functions for generating the memory and the address of the various I/O devices, and in order to control the data transfer between memory and the processor and I/O devices and the processor. So the interface to the external world is done by the bus interface unit. The execution unit, on the other hand, actually receives the instruction codes from memory. It also gets the data from memory and executes the instructions. It stores the result in general purpose registers, or it can store back the result in memory if it is required. So the execution unit does the actual execution of instructions. BIU, interface to the external world. Execution unit does the actual functioning of the microprocessor by executing different kinds of instructions. So this brings us to the end of the 80x86 programmers model. So the 80x86 programmers model, which we have seen, is common for all processors starting from 8086 to 80486. To get a complete idea, you should have gone through all the previous 5 sessions. Only then you would get to know the programmer's model of the x86 processors. So we'll stop with this in this session.